So the presented work is a result of Bartosz Stojewski Master of Science degree plus some extra enhancement due to introduction of a hybrid procedure for solving Ginzburg-Landau equation, and this procedure will be called relaxation method, Schrödinger-Ginzburg-Landau relaxation method. So this work is done at Krakow University of Technology, at Faculty of Computer Science and Telecommunications, and later at Faculty of Electrical Engineering and Computer Engineering, and also at Quantum Hardware Systems company. All right, so let me move on. Yeah, so what's the purpose of this work? Previously, on previous talk, I described the case of, strictly speaking, quasi one-dimensional. But in real life, we have obviously more than one dimension. We have 2, 3, and more dimensions, and there is a necessity to have to treat superconductors from modeling perspective. And those days, like IEST Institute in Japan, they are already able to produce much more than 100,000 of Josephson junctions on a one superconducting chip. And so this is the level of technology development, superconducting technology development from comparable to semiconductor level of development from 80s. Basically, that's how it is. So we will presume that there will be kind of sandwich between sandwiches of different shape between superconductor and non-superconducting materials, and then we will try to extract system features from, try to model system transport of current, distribution of magnetic field, and so on. So that's the purpose of this work, and then you see the certain picture on the left. That's Josephson junction that is biased in general by some external magnetic field coming from 4 black cables. And also on the right side, then there is just another photo of one possible structure existing in rapid single quantum flux electronics implementing classical superconducting computer. All right, and also apart from that, I would say superconducting technologies those days, they have golden time, golden era for development of superconducting technologies. Well, still there's a kind of silver stage of development of semiconductor technologies because they're already so much developed, they don't develop that quickly as they could. And yeah, so this time I will focus more on superconducting technologies. That is also a specialty of my company. All right, so what structures we will treat? So basically, unfortunately, I have always problem with this strip because I don't want to obscure the picture. So we are given certain geometries of superconducting and superconducting material which will be treated, and so we can produce a lattice of artificial superconducting atoms that are embedded in non-superconducting material as given here. Then the systems can be 90 degrees rotation symmetry, it has continuous rotation symmetry, or can be system without symmetry as given here or here or here or here. Yeah. So all these structures will be treated, can be treated by this method. And yeah, so let me partly focus on the field induced Josephson junctions. That was the topic of my defended PhD, and also it's continued, but in slightly different framework of geometries. Yeah, so you see the structures I am dealing with. And let me move first to mathematics, and then later from mathematics move to modeling and to algorithm of solving partial differential equations. So basically, we deal with very well-known theory, that is Ginzburg-Landau theory of superconductivity, that's already from 50s of previous century. That's this theory describes well the phase transition between system being superconductor and non-superconducting, and thus rely on Helmholtz free energy, so for superconducting state and normal state, and this free energy is minimized due to existence of non-zero complex value potential psi. So we have C4 theory here. And so this, in case of bulk superconductor, we have only those terms. And then if we put additional vector potential fields, and which is translated to magnetic field presence, we have two extra terms present here. And of course, as we know, the vector potential fulfills this relation. So we will deal with system described with such functional. And we have one central hint, that the existence of superconducting order parameter that's expressed by density of Cooper pairs is that it minimizes the energy. So this is in physical system, but also it will be used in simulation strategy. And then by minimization of this previously written functional with respect to superconducting order parameter, or with respect to minimization of magnetic field, we come into equations of motion. We have two functional derivatives with respect to previously defined functional, and those equations of motion. So one minimization with respect to fields generates such equation as given here. Another one generates the equation for density of superconducting current flow, which will be shown later. So this is equation of motion, Ginzburg-Landau equation of motion, and this is, if we look on, this is the most simple case without the presence of vector potential or magnetic field. But this equation has certain similarity, so this can be treated as nonlinear Schrödinger equation. And this is nonlinear term. It's proportional. Actually, it's a mistake. It should be modulus v squared times c, but sometimes mistakes happen. And so this is nonlinear term, and this nonlinear term is absent in this Schrödinger equation. So there's a question how to obtain, if we preassume that we have a solution of Schrödinger equation, how to move to solution of Ginzburg-Landau equation. And then such a question is especially valid if this c square term is not so big, if we are close to TC, with transition damage. So our approach will be as following. So we will first, because in general, the Schrödinger equation is a linear, ordinary, or partial differential equation, and since it's linear, it also can be expressed. Actually, it is eigenvalue problem. So this is a very simple problem to be solved. On the other hand, GL equation is not an eigenvalue problem, so it's more complicated to solve it. So so first feature which we want to underline is that number of solutions of Schrödinger equations are infinite due to the fact that there could be superposition of solution that is of previously solutions that is also a solution. So my statement will be as following, that initially we get a ground state solution of Schrödinger equation that is very easily doable, and then we deform this solution in the way that it accounts for nonlinear term, and this strategy is quite simple and quick. So this will be the case. And during this deformation, so we can say this method is nothing else as kind of perturbative deformation of solutions obtained from linear differential equation. So it's a kind of version of perturbative method. So during the process of perturbation, initially we will set beta term to be 0, and then we'll increase steadily, and then we arrive to the solution which we to the beta values that we want to have at final stage. It's also remarkable to notice that during the act of solution, of solution steps, we can also slightly deform the geometry of the system, which will be discussed a little bit later. Just one general remark. So basically, if this VP minus E, VPX minus E is nothing else as alpha coefficient. And alpha coefficient, if we are in superconducting region, alpha is always negative and beta is always positive. It's just a technical message to you. Actually, this will be also greatly discussed in greater detail by another of my students, Łukasz Pruszyński, and he will give you much more insight into that. Okay, so of course, this discretized scheme of Ginzburg-Landau is given here, but you can think about more sophisticated discretized schemes. And then, yeah, so in 3 dimensions, we have such problem optimization of such functional. As I mentioned to you, the equations of motion are obtained by functional derivative of this functional minimization with respect to psi, which is square root of density of Cooper pairs, or vector potential. And in very analogical way, we can define the function. This is already very long existing in literature. We can define the function of Schrödinger equation, and also the equation of motion is, which is Schrödinger equation, is obtained as those by setting those 2 equations and finding their solutions. So one gives you Schrödinger equation, another gives you equation for vector potential, for current density in the system. So basically, current density is the same for Schrödinger equation and for Ginzburg-Landau equation. The only difference is that in Schrödinger equation there is electric charge E, and in case of Cooper pairs, we have double electric charge. Okay, and so let me first show you the case of how to solve problem of Schrödinger equation. I think this is already very well established issue, so I will limit myself to 2-dimensional case. So we have a kinetic term, kinetic and potential terms set here, and then we build a matrix like Trotter matrix with proper tensor product of matrices. So we come into effective matrix of Hamiltonian, and for this matrix there exists eigen state which can be translated to 2 dimensions. So of course, so it's like this problem here is maps 2 dimensions into 1 dimension and then back. So essentially, it's just a single comment solving finding eigenvalues and eigenvectors. So what's the result? Okay, this maybe is okay. So this was okay, and later I applied this method which I mentioned to you. But let's say effective potential is given here in Schrödinger equation, and then wave function is localized. It's when the potential has the lowest value, so it's kind of localized here. So those 2 guys are coming from Schrödinger equation, and then if I turn on beta, I deform this previously defined solution. So that's the case. So this correspondence is quite effective, and well, we do believe that they might be very, very further generalized to various non-equilibrium situations. Okay, and yeah, so then maybe brief scheme how things are. So before I get to one of criticism about relaxation method. So actually, relaxation method has a very long history, and it's a version of gradient method from a certain perspective. But Initially, people used massively relaxation method in Gross-Pitayevsky formalism that is a bit similar to Ginzburg-Landau, but it deals with superfluid cases. And Ginzburg-Landau deals with superconductor, and Ginzburg-Landau has slightly different form. But initially, you need to make an intuitive guess of superconducting order parameter presence, and then you conduct the iterative steps during the algorithm. And but there was always the issue how to get a guess function. And here this problem was solved, because guess function is nothing else. So you might have infinitely many guess functions. Nevertheless, usually they converge to the same solution. But after this improvement into Schrödinger-Ginzburg-Landau relaxation method, we have this problem of ambiguity of a guess function was solved. So that's why it can be seen as particularly valuable in the schemes of solution. Okay, so yeah, maybe. So basically, how things are. So equations of motion. So maybe I will move backward one slide. So this is in ideal case, this is set to 0, but in practical method, it's some coefficients times d over dt times psi, and d over dA times psi, d over dt over a. So each iteration is obtained from those derivatives in this algorithm. There are some papers of my authorship or some other people authorship that does describe this procedure in detail. Okay, again, this Schrödinger equation as shown. So this is this finite different method for solving the Schrödinger equation, and here there's only one comment that you can account for a case of systems that have certain level of symmetry of rotation or without the symmetry. Usually symmetric systems are more easy in solving, and so then it's better numerical stability and better accuracy after all. And then now, yeah, so we make so how things are. We make initiative guess of C and A, and then we compute current densities from formulas, and then we assign some changes of delta psi to every point of the lattice according to the scheme, and we have assigned some changes of vector potential. So how does it work in practice? So we have given the nanostructure by predefined alpha field across the sample. This is case of one-dimensional sample. So you see this that's a superconducting inside, and on other sides there is normal state. And initially we make sometimes in one dimension we can make even stupid guesses, and we finally approach into the proper solutions even for two guess functions. So this was done with case of ambiguity that is already taken away, and then we can see the accuracy of solutions. I'm not underlining that this is the best method from a point of view of accuracy. Nevertheless, this method was tested in extremely hard conditions. I managed to tackle very nasty problem of 5 different physical fields expressed by 5 coupled nonlinear partial differential equations in 3 dimensions with time-dependent case. That was one of the hardest things you can do. And still, this method gives you proper topology of solutions. Nevertheless, it is obviously subjected to certain numerical errors. And in principle, probably it can be still further improved. Yeah, so this is this methodology which I already discussed. So this is what happens. So we take previous value of superconducting order parameter plus the value that comes from this change that is as this. So basically we operate in virtual time, in simulation time, but of course we can also treat time-dependent problems as well. And this is the easiest case of one dimension, and then we can go into further dimensions. During this method, the relative the numerical error is minimized, and let's say and the free energy function is minimized. Then we know that we are going to numerical solution. It's still open issue at which stage we supposed to turn off the simulation and accept the existing values of superconducting order parameter and vector potential. Well, basically, the idea is that the slope needs to have a very small angle of sloping, like 5 degrees, both for numerical error and for free energy functional, and then the algorithm is supposed to automatically cut off further simulation and accept the solution as the most proper one, right? Yeah, so that's the various tests of this method has been done. And yeah, so that's that of families. Actually, what is one archive paper which is attributed to Bartosz Stojewski and me, and you can study it. Just Google me on archive. And what happens if we go too far with the simulation? Well, it might happen we obtained this minimization of free energy functional, but sometimes this is like overlearning issue in neural networks. If you make too many iterations afterwards, it might happen that system energy is rising and blowing up. And so our criteria is to minimize the product of relative error times free energy. So total relative error for a system times total free energy. If it does minimize, is getting the lowest point, we accept the solution over here. That's just heuristics. Nevertheless, this heuristic seems to be relatively well justified theoretically. What structures we studied? Well, various. We have lattice of superconducting squares or superconducting quantumness, you can say. Even with stupid initial distribution function, we come into proper solutions. So this is before this hybrid method was attributed. And then you see how the solutions does depend. So then we have superconductors over here, and during the simulation time, the free energy and average error does minimize. Okay. So 2 dimensions cases are more demanding. 3 dimensions are even more demanding. But 1 dimensional case is usually quite stable. So obviously, it's a good instructive case to study superconductor normal state interface. So half of the space from -infinity to 0 is superconducting, and then from 0 to +infinity is non-superconducting. So we can test this method against analytical solutions, which we know in such a case. It's like kind of kink-like. All right. So this is technology of even before full formalization of this method, during the time when Bartosz Stojewski was doing his Master of Science degree computations, was very intuitive step which was exploited. Due to this nature of similarity between nonlinear Schrödinger equation and Schrödinger equation, if you have let's say, you can have an analytically known solution of particle in 2-dimensional box Schrödinger, and then you can put it as initial guess function, and then, as you see, final solution is the formal version of previous solution, but basically with a kind of same topology. So this is slightly deformed, nothing more. Yeah, again, this is the same story with numerical errors. You can put a lot of criteria for numerical errors, numerical for superconducting parameter, for vector potential, and some other fields as well. But usually you have such characteristic of minimization of error and numerical error and free energy as it is given here. So we have treated various types of structures. So you can have a lattice. So it's like, imagine you have instead of lattice of superconducting quantum dots, you can say you have a lattice of anti dots, so empty places, and on the top you can put normal strip, and then the system as this one can be characterized. So here we have a tool to characterize array of Josephson junctions, and this array of Josephson junctions can be used as antenna or some other for some other purposes. Yeah, and then here is the case of system of time-dependent geometry. So initially we have considered superconducting square, and we make a stupid Gaussian wave package, let's say guess, but during iteration step we deform it, the structure, and we also get very reasonable convergent solutions. So this is a hint that you want to arrive to very complicated, highly superconducting, highly integrated structure. And so you can do it in small steps by increasing the complexity of geometry during simulation time. So this is quite essential here. All right, let me move on. And that's a case, different cases of beta increase in Rhodes coefficient. So we can by step function, and but still results are a bit similar, as you can see. Yeah, so the whole solver was designed, I hope, to test it against more complicated cases, and we'll see how things will go. And then there's also the case of parallelization of this method. Actually, sometimes the numerical error can be used as beneficial factor, because if you can basically, this method has some features with annealing method, so it does minimize the functional. So sometimes to tune up the solutions, use that small noise, and then you see how the system evolves further. But sometimes this noise can be of numerical origin, and this is very nicely surprising that there was the Bartosz-Stojewski incorporated relatively simple differentiation scheme, and he got high level of noise, but this noise in longer time worked. So he got, in parallelized version, he got higher accuracy than in non-parallelized version. That was very nice result. And of course, we can deal with various lattices. We started to, there's a Bloch theorem in condensed matter physics, Bloch wave function, and but this is valid for linear superposition of solutions of Schrödinger equation. And now we can attempt this method, but breaking this linearity. So that's one of the directions of this. So as you see, we tested in various cases, and all these cases, so you can use magnetic field as tuning parameter, and so this two sources of magnetic field can suppress certain level of superconductivity, so we can have tunable Josephson junction if we have set certain external current affecting this state just by vector potential, not by heat. Yeah, so we have some results for that. And then we can also deal with amorphic cases, which is also nice. Amorphic, which means highly non-symmetric integrated structures. So far in 2 dimensions, but there is no much obstacles to go into 3 dimensions. And also we also subject even a amorphic sample to external magnetic field, and then we also test it. So if everything looks fine. Yeah. And that's a case of, for the case of array of field-induced Josephson junctions. Okay, 1 second. So we put a series of non-superconducting strip on the top of superconductor. Then the Cooper pairs flows to non-superconductor. So there is decrease of superconducting density here. So we expect Josephson junctions, and indeed, the simulations we get lower values of superconducting order parameter over here. And also this system can be subjected to magnetic field as well. Yes, so we really tested. So from certain 2-dimensional case, I've not fully yet tested with this full Schrödinger-Ginzburg relaxation method, but we are very close to that. So you see that this thing works. And then we have a case of banded cables. Let's say, okay, banded cables. So banded cables actually increase some external modifies alpha value. So it is this banded cable is seen as an effective barrier. This has already emerged in my previous talk, but here we also deal with. We expect that in case of banded cables, we have there is not Meissner, and this geometric Aharonov-Bohm effect. So what we are saying is banding of cables introduces imaginary complex value vector potential. I mean, from Jackson book, you know only about real value vector potential generating real value field, but here we also deal with imaginary part as well due to geometry. So this is valid for both, for the case of superconducting nanowires and superconducting nanowires. And then the last question is how to generalize scheme further. Well, by using Weyl-Dijon equations. So we arrived into Ginzburg-Landau solutions and we plug it as initial solutions to Weyl-Dijon's, and then we get quasi-particle behavior in the system, which we can go much deeper into macroscopic properties. So this can be even exploited for vortices, which were also described at the early stage of this day. And of course, we do hope to have very universal algorithm against very generalized Ginzburg-Landau equation, which we have S, Px, Py, and the order parameter. So we claim to have a method to attack such problems as well by this initial guess using Schrödinger equation and ground states and a solution of Schrödinger equation. That's how it is. So that's what we do hope. So we hope to be able to minimize such functionals. So far, first tests already did during my PhD was rather successful. So there's no reason to be pessimistic, I would say. And that's a bibliography. Now there's one publication under review with Barton. We've already defined masters. It's no longer master student. He was master student, Barton Stojewski. All right. There's kind of a lot of my work in compile about random access memory in rapid single quantum flux computer. You can see those things, and yeah, thank you for your time and attention. And